Yeah, I should say that I actually started with machine learning when I was still a biologist, because these days modern biology has very little to do with plants and animals, and more with pattern recognition and looking at vast tabular data. But it's true, these days I do more IoT things, so I'm more technically minded. And I phrased this talk computational decision making because I have to admit I even try to avoid to use the term machine learning because it usually raises the expectations of what's going to happen. And as soon as somebody mentions machine learning, it's not far that somebody else mentions artificial intelligence that I really don't like as a term. And so, yeah, I try to keep that out as much as possible. For further expectation management, this talk aims to provide you with a sort of basic vocabulary. So if you are not coming from a computer science or machine learning background, what are the sort of words you might hear during those 2 days? I'd like to introduce a couple of very fundamental concepts of a computational decision making, phenomenologically introduce you what it looks like if you use those methods, and give you a rough idea when to use one or the other method. Can I just see a show of hands who of you considers themselves a machine learning practitioner? Wow, very good. Because this is not a hands-on tutorial. This is not a thorough summary. It's not a comprehensive guide. We're going to stay very much at the surface. If you are a practitioner, you would be very disappointed, okay? This is not a technical deep dive, so you're not going to learn about parameter tuning here. And it's also not a statistics course. That being said, I can start. So, although you're not machine learning practitioners, I assume there are a couple of programmers here in the room. Can I see a show of hands for everyone who considers himself a programmer? Oh yeah, it's probably the majority. So, there's a small code snippet. You would enter a word, and the computer would respond whether that word exists somewhere in a dictionary. Is that artificial intelligence? Oh no, the dictionary can be quite thick, but it's not artificial intelligence. Yeah, this is just a piece of code. Next example. We are asking for a temperature. The user enters the temperature, and then the computer will respond whether I should wear shorts or long underwear. Okay? Very simple. Is that machine learning? Well, everyone disagrees. Very good. This is not machine learning. So we're going to start with a first definition here, and that is any rule-based decision-making on the basis of a numerical threshold or by a pattern match to a dictionary, anything like that. That is not machine learning. And that actually gave rise to me once writing a blog post about what is computational decision-making, because a friend of mine said, like, you know, the phone just told me that I'm in Caracas and I'm not. That's a machine learning fail. And I didn't know whether if the phone made that assumption on the basis of a string match or probably on a geographic location. But I was very sure that it was not machine learning. It was really just a simple decision that the phone would make at that very point on the basis of some input. So it's not machine learning, and it's definitely not artificial intelligence. But what if? What if the threshold for making that decision, whether somebody is in Caracas or should do X or Y, is inferred at runtime on the basis of data? So assume that rather than querying for a distinct temperature, I'd say, well, input a table. And that table should say, for example, distance from Houston Station and price of property. Okay? And my program is supposed to make an inference, so write a software that says how close to Houston you can live, you can afford to move, if you want to spend 650K. So that is public data. So essentially, if you just look at the distance that you can travel with the Northern Line from Houston, northwards. Right there, Houston, property price roughly over $1 million, okay? You go out all the way to High Barnet, property price still about 500,000. And you could probably guesstimate, like, if you have 650,000 at your available, you can probably afford to live somewhere here. That would be your decision making. It's simple maths. You've all seen it probably in college. So that's called linear regression in that case. And it's probably the most simple machine learning method you can think of. And this is something you shall see over and over again. So if you come from a maths background, you will identify that many things that statisticians have been talking about for decades is now being sort of rephrased in artificial intelligence lingo. Okay? So here in that case, it's an example of supervised learning because we are teaching the computer the relation between an input variable and an output variable. And here in that case, it might be a linear fit. So y equals mx plus b, and that's easy. So in maths, we might call that like an input variable. In machine learning, we call it a feature. The more features you have, the bigger is your choice to find something in that data set. And we have an output variable. In that case, we call that output a label. Okay? Now, linear regression can be arbitrarily complicated. So rather than just counting the number of stations from Houston out to High Barnet, you could say, well, how large is that apartment that you want to buy? Okay, that gives us another dimension. So here's that distance from Houston to High Barnet. This is the size of that apartment. And you see that we're essentially spreading out this plane. And that helps us to estimate the price of the apartment. And again, the difference between curve fitting in statistics and machine learning is probably just semantics. Now, rather than using a continuous variable like the price of that apartment, what you can do is you can assign an input to an output class. So essentially, we are assigning so-called class labels. The canonical example everyone in the machine learning field is using is essentially here the Fisher's iris data set. So there are these iris flowers, and there are sepals and petals. So there are different types of leaves on the flower. And each of these three different types of species are essentially different in their ratio between the width and the length of these sepals and petals. Okay? So when being shown the size of those leaves, a computer can decide whether it's Iris reginica, Iris setosa, or Iris versicolor. Okay? So that's a classification task. So we're going to take an input matrix, and those input matrices have to be complete. You can't have missing data, and this is one of the reasons why when you come from the data science side of things, you first have to spend an awful lot of time cleaning your data and making it complete before you can actually work with it. So then we have these class labels. So the computer has no notion of irises or whatever, so we say, if it's this one species, it's class 1. If it's the other species, it's class 2. And yet the third species is class 3. Okay? Then we have these different features. Of course, again, the computer is not interested in sepal and petal and width and height. It just wants to see the data. So there might be non-numerical features. For example, a smell, a description of a smell, the name of a color that we're seeing. That needs to be encoded as a number. And there are various strategies to do that, but you cannot really feed in a string. The computer has no notion what that means. So let's say we're just taking sepal length and sepal width, and we would do a scatter plot. So essentially, we plot one variable against the other. And what we might see is that we can separate these two classes here, iris virginica and iris setosa, by just drawing a regression line somewhere here and saying everything that's essentially above the line is virginica, what's below the line is setosa. So that's what we call separation of class labels. And essentially, we are using a function that takes in these input features, and we make a projection into one class or the other. So as simple as that. Now, we have more than two classes. We have three classes. And of course, we have a lot more variables. So we do not only have sepal length and width, we also have the petals. So something's going to happen. Now, what if we first make a split across our first sort of regression line to sort away the iris virginicas, and then we're only stuck with iris setosa and versicolor, here shown in yellow and blue. Okay? We could then have the next sort of regression line here and say, well, everything that is above is roughly going to be setosa, everything that is below is roughly going to be versicolor. If you do that, you end up with a decision tree. So that's one of the methods that's being used in machine learning. Now there's a problem, because you can do this again and again and again. You can add more decisions and be very, very specific as to how you would like to separate this data set. And you can play this game forever. Unfortunately, you are then overfitting your data, so the computer cannot generalize your description to the data that's out there, and it would always be able to tell very nicely how to separate those three classes on the data that you've already shown it, but if you show it new data, it doesn't know what to do. Okay? So therefore, there's a method called random forests. And with random forests, you just take a random subset of that input data, and you make this sort of guessing game as to where you go left and right on a subset of the data. And you repeat this many, many thousand times, and then you build a consensus as to what gave you the sort of best predictions. And that is one method against this overfitting. So overfitting, I can roughly show this here. So we've seen that these two species cannot be perfectly separated with just a linear fit, okay? So we have to find some sort of compromise. If we put our regression line too high up, okay, then it's a sloppy fit. That is underfitting. That might be a good compromise. And here in that case, where we really try to get to the best possible prediction, although we cannot generalize that, that's called overfitting. And there are methods called L1 or L2, regularization, that essentially either reduce the number of features you take into account for doing your machine learning, or you say you cannot have any extreme weights, like, that you penalize something very, very highly just in order to get that fit correct. A method commonly used for machine learning is dimensionality reduction. And the intuitive example here is that previously I've shown you always the separation on the basis of this scatter plot of sepal width and length. But we totally forgot about the petals, right? So we can take this higher dimensional feature space, and we can condense that information into a two-dimensional plot, for example. So this plot here would really represent how close these data points are together if we would merge our data set to just these two dimensions. That's done with a method called principal component, in that case, analysis. So the principal components describe which variables in your data set contain the most information to separate your classes. Very often, you'd use such a principal component analysis before you then move on to another method, for example, the support vector machine. So again, we're trying to fit some sort of regression line to separate our different classes. But the question is, which of those three lines makes a good separation? There is no rule, really, that would describe that one is better than the other. You might see a couple of problems if you are very close to a particular data point. You might think, well, you know, if I don't get this regression line correctly, then I might misclassify. But there's no systematic way of dealing with that. So this is where the support vector machine comes in handy. So essentially, you take the input data and you define parallel lines that sort of are in touch with the input data, and then you derive the perfect separation between those. But then you don't make this a hard line, but you allow a little bit of leeway left and right. So these are essentially margins, okay? The separation happens here. And that gives you essentially the space to consider input data that you haven't seen yet that is still then being classified correctly. One thing you might hear about is the kernel trick. So, as you've probably seen, there are some classes you can just not separate linearly. It's just impossible. Now, you can project your data into a higher dimensional space, and an intuitive sort of visualization of that is that imagine that you have a two-dimensional input space where you can't really make a linear fit in order to separate the red from the gray dots here. But then, if you would, by some mathematical magic, project those points into a three-dimensional space, then you'd be able to draw a plane between those and separate those dots again. And there are different mathematical ways of doing this, coming from nonlinear optimization. For example, the radial basis function or the polynomial kernel. And when you then project those back into what I've shown you in the support vector example, you get these sort of very irregular shaped polygons that describe where your data is being separated. So how do you do this generally? So the general approach, and I take this from real life, is that you have your features, and I assume all of you have sat in an airplane before, and like when I have to fly, I'm always a little bit anxious because I don't know whether my flight's really going to leave. And snow can be a problem in many parts of the world. So features I'd look at when I think about whether my flight's going to be cancelled or not is probably the weather forecast, the airport location, the number of gates and runways as an indication of size, because flying out of Cambridge might be more complicated than flying out of Heathrow, the number of snowplows they have, the airline I'm flying with, maybe the aircraft. And then I have a training step. So the training is essentially my previous experience that I've gained throughout my life. So I feed all of this information into my black box. And what comes out is this classifier. And this classifier sort of encodes the relative rank, how these features are important for me to decide whether the flight's likely to be cancelled or not, maybe weights for the features. So if I know that there is a huge sort of imbalance between the number of runways and the number of snowplows they have, I know that if weather or if snow is forecasted, I'm more likely to be cancelled, okay? And that then leads to a prediction. So I'm showing new data to my mental model, and I then make, on the basis of my classifier, the assumption whether the flight's going to happen or not. And that's effectively what we're doing with the computer. Now, how do we decide whether that classification is reasonable? So one example are these curves here. And here, I'm plotting my true positives against my false positives. So I think about the 100 times my flights were cancelled in the past. And I then show these information to my classifier, and I find out, for example, in order to predict 80% of those flights correctly that were really cancelled, I have to accept that about, say, 15 to 20% of the flights that have not been cancelled will also be flagged up as potentially being cancelled. Okay? Very often when you do machine learning, you get a variety of these curves for different parameter sets that you are initializing your machine learning method with. And your job as a machine learning practitioner then is to choose the method and the parameter set that gives you sort of like the best performance. Now, if your curve isn't that nicely shaped and goes up very steep, but it's probably just a diagonal, that's probably as good as a random guess. You can just flick a coin. It's cheaper. If you fall below, that's worse than a random guess. There are some cases where you just cannot tell why your classifier can't work. So then there's the easy trick that you just do the opposite of what the classifier tells you to. So we do training, we have the classifier, we feed it new data, we do the performance assessment, and we ask, well, is this good enough? If it is good enough, well, success, we can go. If it's not good enough, we need more training data, we need to optimize our parameters better. And there's an entire zoo of different metrics, and I'm not going to read those out to you. But always think you have a positive class, so flights that have been cancelled. You have a negative class, flights that have not been cancelled. Now, do we predict the flight to be cancelled? So those are our true positives. Or do we predict it not to be cancelled? That would be a false negative. Or we have false positives and true negatives. Now, depending on what you want, certain combinations and ratios can be critical. So if you have a problem in the medical field and you can absolutely not afford to have a false negative prediction, then of course you choose a metric that penalizes that. Now, if you have a question where you are very much agnostic of what comes out, then you might simply go for, well, the metric that I just showed you in the last slide. So typically, in a machine learning pipeline, you have a data acquisition step or a data lake that's already present. You then go into model building, and then you test your model. Within model building, you have the raw data, you have to do the cleanup, and you will hear that number very often. 80% of a data scientist's time really goes into cleaning up the data. We're awfully expensive for somebody who just cleans. We then do feature engineering. So essentially, you look at the problem and you decide which of the different properties can you use for a machine learning prediction. So in case of the irises, we just had sepal and petal length and width. Smell might be another one. So feature engineering is really where you probably invest most of your time into. Then you learn your model. That's quite compute intense, but can be fast if you can parallelize. And then you choose a model on the basis of those metrics that I've shown you before. You can then use your machine learning model in production, but it's very often important to continuously evaluate and monitor the performance of your machine learning classifier, because there might be seasonal effects. If you have learned something during summer, your model might not apply in winter. If there's some sort of direct or indirect dependency on temperature, for example, and you might not know or think about that in the beginning. So it's always worth to have a look at your performance over time. How do you choose a machine learning method? So just recently, a paper came out that assessed different machine learning methods in the context of computational biology. So a proper shootout, 165 different scenarios, and then they ask how often did method X beat method Y, okay? And yeah, there are a couple of methods that continuously perform better than others, but it is not a definite truth. Also, the choice of a machine learning method depends on things like runtime, interpretability. So for example, if you shoot your entire variable set, your entire features into a dimensionality reduction, and then you do a support vector machine, what comes out of that cannot be easily interpreted. The classifier might be very good, but you can't really tell on the basis of which of the input features your classes were separated. Whereas if you use a random forest, a decision tree, well, it's there black on white, more or less. Yeah, it's the ratio of sepal versus petal width and height. I've avoided them. What about neural networks? Everyone's doing neural networks these days. So neural networks attempt to mimic the integrative properties of nerve cells. So here, nerve cell, cell body, receives a lot of inputs, makes some magic computation, and that magic is true, be it computational learning or actually happening inside the brain. Of course, we don't really know how that all works. And then we have outputs. So the single smallest entity is a perceptron. So that's mimicking the behavior of such a nerve cell. So what you would have is input features, and those input features will have a certain weight. And on the basis of this input function, you might probably have something like weight 1 times input feature 1 value plus weight 2 times feature 2 plus et cetera, et cetera. So that's our input function. And then we have an activation function. So essentially, it's a x versus y decision. And that x versus y decision determines whether our neuron is going to fire or not, or whether we assign our input, maybe the irises, to versicolor or reginica. Now, if we have an error here, we can use that error to update our weights until we reach a performance of our perceptron that we're satisfied with for a simple classification. Now, the exciting bit really about deep learning is that you combine many of those perceptrons to larger agglomerations. And by doing so, you achieve very complex behavior. So whereas a linear regression that I showed previously would just draw like a straight line through your data, you get very complicated landscapes in that sort of plane of your data, how separation can happen. Depending on the task, you can then say, for example, all of your input values here might be pixels from images, okay? And just by training your neural networks on certain output classes, you can then define whether it's seeing a cat or a dog, okay? Now, there's again the problem with interpretability. So it is a very active area of research to decide how neural networks actually achieve their superior classification performance. Again, it's just what I said about the support vector machines. It's very hard to then say, this image has been classified on the basis of something in here, because it is very abstract how classification actually happens. Something that I haven't seen in the agenda for the conference is reinforcement learning, and I would have been very thrilled to see something like that. In reinforcement learning, the methods learn iteratively how to optimize a certain task. So here, in a now already classical example, the machine was being shown images of space invaders, okay? It was given a score. Now, an image from space invaders, essentially a pixel map, 210 by 160 pixels, 8-bit RGB. And the computer had to decide whether it wanted to move left or right or shoot. Those are the 3 activities you do when playing Space Invaders. The task was to do something that increases the score, so to be a good Space Invader player. But that was then achieved by iteratively training, essentially online, how the input, so random movements in the beginning, lead to better achievements in the game. And over time, the computer then learned, being shown various different pictures out of the game, what to do. So I find this is really clever, but this is also very compute intense. So we're quickly going to go through unsupervised learning. So everything that I've shown you so far is supervised learning. So we show the computer, prior to us really getting on with our work, a relationship between input and output. Now, unsupervised learning is being used to explore data that you might not have seen before, that the computer hasn't seen before. There are different methods, for example, hierarchical clustering, kmeans clustering, expectation maximization, and density-based clustering. They're usually combined with a clever visualization of the data, so you get a notion of what's actually going inside your data set. So this is an example of hierarchical clustering. And what you're trying to achieve is you sort your input data on the basis of similarities. So you can think about those dimensions of sepals and petals as little vectors, and you just calculate the highest degree of correlation between different input data. And what you would find here in this case is that apparently there are 3 different classes in our iris data set. So here in that case, we didn't tell the computer that we are after 3 different classes, but visually it becomes very evident that there are 3 different classes. Or I should say that the different columns here mean sepal width, sepal length, petal length, and petal width. And those dendrograms show the relation, how similar these different input features are to each other, so how much they correlate, but also here along this axis, how far the little individual data points correlate with each other. There is a method called kmeans clustering. You can combine kmeans clustering, again, with dimensionality reduction. And here in that case, we would then ask, well, if we can place a centroid, 2 centroids, somewhere here into that data, how can we achieve that all the data points fall as close as possible to one of these 2 different centroids, or 3, or 4, or 5, okay? And by going through a different number of centroids, we're trying to force the computer to assign the data to, we can then find out, for example, here in this case, the distance of individual data points, if we just have one cluster, if we just have one centroid, is quite large. And, well, apparently, if we have 3 classes, then we get the best sort of assignment to individual data points. If we increase this to 4 classes, there's not much gain. So it gives us a notion that 3 classes might be the optimal number to then look further into. In the interest of time, I conclude. First conclusion, tongue-in-cheek. People on the internet steal infographics. So this is the one I made for this original blog post back in the day. I've seen it used again and again by other people without credit, but yeah, it's mine. Machine learning methods have been around for ages. It's just that statisticians called these things very differently. And it is really with the availability of large data sets and with the availability of raw compute power that we're now able to really to do that in practice and not just leave it to academic mind games. And I think that understanding key principles behind machine learning, just the way that I presented that today, should really be part of the school curriculum, because, I mean, algorithms rule the world, and everyone deserves to understand what's going on. And with that, I'm happy to take any questions.